Assalamualaikum, hi students. So today let's continue with turbine, compressor and throttling device. So first let's look for turbines. So turbine drive electric generator in steam, gas and hydroelectric power plants. So here I draw the how steam how turbine will operate. So basically inside the turbine there are blades, okay? Then the blades are attached to shaft. So shaft will rotate and then the turbine will produce power. So that's the key different thing with compressor. The image here, this one is for compressor. Compressor, pumps and fans, they require power, okay? Power input to operate, okay? Work is supplied to this device from external source through a rotating shaft. So their function are about the same but different application. So fan will increase the pressure of gas slightly and is mainly used to mobilize a gas. Compressor compress the gas to a very high pressure, while pump is almost like compressor, except pump will handle liquid, not gases. Okay. And here, this is the energy balance for turbine. So basically for turbine, normally they are well insulated. So your delta Q equal to 0. But since you want to produce power and work, so you need to have additional energy from kinetic energy and potential energy. So you have to these two terms in your equation. So your final equation is M H1 plus V1 square over 2 plus GZ1, okay, equal to W out power plus M H2 plus V2 square over 2 plus G times Z2. So this is your final equation for turbine. While for compressor, normally you have W in, so your W term is at the front, and normally you have heat loss. Okay, so you have to consider Q out. And there's no kinetic energy and potential energy for compressor. So your final equation for compressor is W dot in plus M dot H1 equals to Q out plus M dot H2. Alright, so now let's look at some example. So this example is for compressors. Air at 100 kPa and 280 K is compressed steadily to 600 kPa and 400 K. The mass of air, the mass flow rate of air is 0.02 and your Q out is 16 kJ per kg. Assuming there's no change in kinetic energy and potential energy, you need to determine the necessary power input of the compressor. So first, make a habit to write down the general energy equation. So this is the equation for compressor. So you need to rearrange this term, okay? Because the Q out is given as kilojoule per kg, so you need to write like this, okay? And rearrange so that your power input at the front. So Win is equal to M dot Q out plus M dot H2 minus H1. Okay, since we are dealing with air, so you need to look at table A17. Okay, so H1, we need to find H1 and H2 from table A17. H1 at T 280K. Okay, you need to look at the value. So you get 280.13 kJ per kg. And H2 at 400 Kelvin is 400.98 kJ per kg. So now you already have your H1, H2, and Q dot, Q out, and M dot. So you can solve for W in. So just plug in all this information, this is number, in this equation and solve for power input. So your power input is 2.74. It should be kilowatt, okay? Kilowatt here. Kg cancel out, so you left with kilojoule per second is kilowatt. So the power input to the compressor is 2.74 kilowatt. Now let's look at example for turbine. Okay, power output of an adiabatic So recall that adiabatic is Q equal to 0. There's no heat transfer. Steam turbine is 5 megawatt. Okay. The inlet and exit condition of the steam are indicated in the figure. So it's given here: pressure, temperature, velocity, and Z. Okay, so this one. And at the outlet, you have X2. Okay. So you need to compare the magnitudes of delta H, delta KE, and delta PE. B, you need to determine the work done per unit mass. And C, calculate the mass flow rate. Okay, so first, since we are dealing with steam, so you need to look at steam table. So this high pressure and high temperature, this is superheated vapor. So you need to look at table A6, while at the outlet you have a mixture, so and pressure. So you look at the value from table A5. So from table A6, your H1 at this condition, 2 MPa and 400 degrees Celsius, H1 is equal to 3248.4 kJ per kg, while your H2, since they give you quality, so you need to use this equation. Okay, H2 equals to HF plus X, HFG. Plug in here, okay, and you will get H2 equal to 2361.01 kJ per kg. Okay, so now you already have your H2 and H1, and you calculate for delta H. Okay, delta H equal to H2 minus H1. So you will get delta H equal to negative 87.39 kJ per kg. And next, we want to calculate for delta KE. The equation is V2 squared minus V1 squared over 2. So velocity is given, okay, so just plug in this equation, but don't forget, you need the answer in kilojoule per kg, so you have to divide by 1000. So plug in this equation and you will get delta KE as 14.95 kilojoule per kg. Okay, settle. Now delta potential energy, the formula is G Z2 minus Z1. Okay, Z also is already given in the figure, so you just plug in. G, gravitational force is 9.81 meter per second squared. Z2 6 minus Z1 10 meter. And remember, you need to divide by 1000 to convert m to m squared per second squared to kilojoule per kg. Okay, so once you divide by 1000, you will get delta PE as negative 0.04 kilojoule per kg. Okay, now let's look at part B. The question asks for determine the work done. Okay, first you need to rewrite the equation, the energy balance equation for turbine. Okay, so it's M H2 M dot H1 plus V1 squared over 2 plus G Z1, okay, equals to W power out over M. Okay, initially we don't have M, it's power, okay, plus M dot H2 plus V2 squared over 2 plus GZ2. Okay, so now we don't know the mass flow rate yet, so it's simpler to cancel out this M term, and this you need to divide by M dot. Okay. So to get the work done, because the W dot term is for power, so then is small w, and then you need to rearrange the equation. Okay, put W out at the front, so W out is at the front, so you need to bring the H2 term to this side, so it become negative. So H1 minus H2 plus V1 squared minus V2 squared over 2 plus G times Z1 minus Z2. So we actually have calculate the value before this, okay, but the one that we calculate is opposite, okay, H2 minus H1, V2 squared minus V1 squared over 2, and G Z2 minus Z1. Okay, so we have to convert, make the sign opposite. So Initially we have delta H as negative 887.39. So now we have a positive number. Positive, and Ke make it negative. Potential energy make it positive. So your final W out is equal to 872.48 kilojoule per kg. Right? So last part C, the question asks for mass flow rate of the steam. So you can use the relationship here to calculate for your M. Okay. So power divided by work done is mass flow rate. So power is given as 5 megawatt. So it's 5,000 kilojoule per second. Divided by your work done, 872.48 kilojoule per kg. So kilojoule cancel out. So your M dot is 5.73 kilojoule per second. So this is the final answer. Okay. Now let's look at the last device, throttling device. So throttling device is any kind of flow restricting device that cause significant pressure drop. Okay. What's important here is the energy balance is H2 equals to H1 and H is equal to U plus P1 V1. So here there's an example. So your H will remain the same. Your U1 and P1 V1 can change, but their total, your H, are the same. And normally the other name for throttling valve is isenthalpic. Okay, where isenthalpic is equal to enthalpy. So you have to remember this. H1 is equal to H2. Okay. So there are three types of device, throttling valve, adjustable valve, porous valve, and capillary. What's important here is you have to remember that it will cause significant pressure drop in fluid. Okay, and another thing to point out is for ideal gas, okay, T remain constant, but for other fluids, since they are a huge pressure drop, your T also will change. Okay, I'll stop here and we'll continue